So I'm going to create example. And I'm going to use these two vectors. Make that look a little nicer. I'm going to call this one U. I'm going to call this one V. And I'll throw a third one in there, W. All right. And that's going to be something in the ever so slightly negative direction, maybe a little longer. All right. So the example involves these given vectors. And if you do it, the expectation is that you do it to scale. Right? It doesn't have to be precise, but whatever the length is of W on your piece of paper, that should be the length that you use throughout the exercise. Right. So I'm not saying that you have to put a piece of loose leaf up to the screen and trace it out, but that might not be the worst idea ever. Right. So we're going to graphically find each. And I'm going to say for the first part, I'll keep it as simple. U plus, I'll go with W. For the second one, I'm going to say 2U minus V. And for the third one, I'm going to do, I'm not going to make it too crazy where you have like more than two components, at least for the graphical ones, because, it doesn't really add anything to the conversation. So I'm going to say 2W minus U. All right. So I have my just three components, three pieces to this. I'm going to, for each one, I'll create a separate graph because last time at the end of class when I did it all on one, and that could be a little much. So I'm going to do A first, the U plus V. I'm sorry, U plus W. Draw a set of coordinate axes. All right, I'm going to take U and bring it on down so that it's pinned at the origin. All right, I'm going to take V and do the same thing. Pin it at the origin, and then we're going to find the vector sum. The vector sum is what you would get if you took the tail of one of the vectors and put it on the tip of the other. All right, so I'm going to take my W and put its tail on the tip of U. All right, so even with only a couple of vectors here, it can get a little messy. Just move those around. But what our vector sum is going to be is what you would get if you connected this endpoint here with the origin and threw a little arrowhead on it. All right, so that red little bit there, I'll get the arrowhead off of that. This is U plus W. I think I might have said U plus V a couple of times just out of force of habit. Right, but that would be what we call the resultant vector. Right, and so this is used in physics a lot, where you have forces being pulled in opposite directions, but not entirely opposite. Like you have some object that's pinned here, that's being, and a force, maybe a wire is attached to it and it's being pulled in this direction, and then another wire being pulled on that in that direction, and maybe it's only tied down with a bolt. So it's like, well, what kind of strain are we putting on that bolt, based off of the angle? And would there be an optimal angle to place my U or V, U or W, in order to make it, put the least amount of strain on that bolt that's holding it in place? Okay, so that's just a small application idea or example. The second one, I'll do it over here. B, again, coordinate axes. I'm going to need two of the U's. I'm going to take one and put it at the end of the other. U plus U is 2U. All right, so I'm going to create a brand new vector here that's called 2U. All right, now I need negative V. Negative V is just V, but in the opposite direction. All right, so if I take what I have for V, and take the arrow off of one side, but put it on the other, I just went from having V to negative V. All right, so that would be my new vector. Now, the one thing we talked about, and I'm actually going to move this down a little bit. Oh, I'll move it down here. I'll do what I did before and actually write the problem again. 2U minus V is the same as 2U plus negative V. All right. So what we're actually finding here is another vector sum, but with a negative V as opposed to a positive V. Right. So we would do the same thing. We would take the tail of one of them and tack it on to the tip of the other and connect to the origin. All right. So I'll use red as my default resultant vector color. That doesn't matter. Color is great. It really helps, but as long as you label it up good, then you're fine. All right, so my red vector here is 2U minus V. And with that in mind, I realized my example for C is pretty much exactly the same thing as what we just did. So let me change that up a little bit. I'm going to go with, yeah, I think I could do that. 3W minus 2U. All right, so, scaling it up pretty good, but nothing too crazy. Like, I'm not going to give you like 45U, that was like, you need a poster board for that. So I'll take this and kind of chuck it down below. All right, coordinate axes, just kind of do it sort of in the middle and then move it if I need to. I needed the W and the U, so I'm going to replicate those, bring it on down. Now, again, if you're having the thought like, oh, this is great, you could do it on the iPad with a pencil and it comes out nice. How the heck are we supposed to do it? When I give you a problem for the test, I'm going to give you 3 line segments. You just produce those on paper and then just take the edge of like a Post-it note or an index card and just take it and put it up against the length of the vector and just slide it down so it preserves its orientation. Right. So, I mean, I just waved the Post-it note at you like that was going to be very helpful, but you've done stuff in the past, whether it was, I mean, honestly, it was probably in elementary school that you did it, where you needed to figure out using a map and the scale at the bottom of the map, how far it is from New York City to Pittsburgh. And how did you do it? You took the side of an index card and you marked it up as the distance 500 miles, and then you just traced along the path, a straight line path from New York to Pittsburgh. And then you found out how many of those 500-mile increments you needed, and that was it. That's the same idea here. You're just going to use tick marks to help you get the size and orientation of it. All right. But in this case, I need 3 of the W's. So one here, another here, And I'll just take this one for good measure. All right, I'm going to use the orange to identify. Oh, that would have been nice. Okay, well, I'm going to use a little trick here. I'll get it on there. All right, so this one is now 3W. Now I need a negative 2U, but remember, it's really a vector sum. All right, so that negative 2U I could think of as, just making sure I'm going the right direction and not taking up my own space. You can think of this as 3W plus 2 times negative U. So two of those negative U's, twice the length of the negative U's. Well, I have a positive U. I want a negative one. So I flip the direction of the arrow. So that's my negative U. And I'm going to pop that in twice. 1, 2. All right, so this new line segment here with an arrow at its head to make it a vector is negative 2U. All right, so now what I need to do is use my tail to tip method, but I didn't leave myself with much room. So I'm going to resize here a little bit. Oh, actually, I can't resize. I need to preserve the size of the vectors. So what I'm going to do is I'm just going to move this over a bunch, just so I have enough room to get it in. And that's one of the things you might have to deal with. You draw a nice big graph with all the like long line segments, and you realize you're out of room. You just crumble it up and do it again, unfortunately. But in this case, like if you have the means, I mean, for a topic like this, if you have an iPad, you have a stylus, doesn't have to be anything too fancy. You could actually pull this off using technology. All right, so it's up to you though. Most people in the past have wanted to do it using just pencil paper, so that's fine also. So I just took my negative 2U and slid it so that its tail was at the tip of the positive 3W, which is now in the way, so I'm going to move it, but I didn't know that going in. So, and that happens too. Like, labels are great. They really help identify things because that's what labels are for, but sometimes you make the label and then realize that it's right in the way of where you want it to be. So on the test, I would say you could hold off on labeling things until after you've created your final product, or do it, write it lightly in pencil in case you have to erase it later on. All right, and so this point to the origin is my resultant vector. All right, something that nobody asked, but I got to imagine somebody's going to wonder at some point. The arrow will never be pointing at the origin. It's always going to be pointing away from the origin, right? So label it up with 3W minus 2U, and that would be my resultant vector. And out of context, it's like, oh, okay, what is this, art class now? Well, if it is, it's not a very good art class because you've seen my diagrams, but it does have a practical application, and doing the drawings helps to really kind of drive home what the relationship is between two vectors, right? Because it's not just magnitude, it's direction. And sometimes, like we take the sine of 30 degrees, and maybe that that's equal to 1/2, but where is 30 degrees? If you're not familiar with the unit circle, you wouldn't know, right? And this is all unit circle related. It just doesn't seem that way right away, because what's happening here is we're creating angles that if we take a step back, just go back to the beginning of the previous unit, I would have a 0 degree over here, 90 degrees over here, 180 degrees over here, 270 over here, and then back to 360 over here. So I now know that if I have this vector sum, 3w minus 2u, I know that its resultant direction is going to be in the third quadrant somewhere, right? Looks like it's pretty close to 225 degrees, but it's not, just based off of the way I designed the problem. But it's in that neighborhood. So if a question said, in what direction, which of the following directions is closest to the resultant vector's direction? Like if I gave you a choice of, I'll give you 4 choices, 1 in each quadrant, so 42 degrees, 138 degrees, 220 degrees, or 311 degrees. Like you would choose the one that's in the third quadrant, right? So I haven't asked that question in the past, but I feel like that's a nice question to add. So when I make the practice test for this unit, I'll try to remember to throw that bad boy in there, because I like to revamp my tests every semester. So part of it has to do with not being predictable. That's like 10% of the reason why I do it. The other reason is because as I teach a course, I kind of get a feel for like the population of students, and I sort of tailor the assessments to the what I perceive to be the strengths of the students. So, and so therefore I emphasize certain things. And if I emphasize it in class, then it kind of makes sense to put it on the test. Like I always hated when teachers, and it didn't really happen very often, but a teacher would say, "This is really, really important. Trust me." And maybe even throw in a wink. And you're like, okay, this one's definitely going to be on the test. And it wasn't. And you're like, oh, so you're just being a jerk? No, they just thought it was really important. They weren't sending any messages, but the interpretation was that they were giving a hint. I'm not even giving a hint. I'm flat out telling you this concept will be on the test. So you want to make sure that you can do the diagrams, because there's so many times in the past where I'd have people just done and expect full credit. I'm like, you're not even getting 1 point for that. That's not even closely related to what we were doing. Okay, so you got to kind of take my word for it at this point, but I promise you it will be on the test. Okay. And additional applications of it too, which makes it more interesting. All right, so let's go back, or continue. Magnitude of algebraic vectors. So we kind of got into direction in a very rudimentary sense. We didn't talk about the direction as a precise value that's coming. We're talking about it in the sense of, all right, is it going up and to the right, down and to the left, and so on. But we also want to know how long the vector is, right? The length of the vector, is the vector's magnitude. Now, without context, it doesn't really have much meaning, where you say something like, okay, the magnitude of the vector is 11. Like, okay, so it's 11 units long. Great. What does that mean? But if I tell you vector, in this case, vector v, -6, 8, all right, so has an x component of -6 feet and a vertical component of -8 feet. Now you have feet as your units of measure, and that'll give you an indication of the magnitude. All right. So in A here, it says find the magnitude of vector v. All right. So the notation is we use a double bracket, double vertical brackets, kind of like a double absolute value. Some people just use single absolute value to represent the value of the vector. The problem is that sometimes confuses people. right? And really, I mean, it's just kind of a different way of doing things, but and so it really shouldn't. But what people interpret this as is the absolute value of this vector, which you might think is 6, 8. But that's not correct. All right. So that has nothing to do with this. When you talk about the value of a vector, absolute value of a vector, you're talking about this relationship here. It's really the length of the vector. All right. So let me get rid of this because it's an eyesore. I'm going to plot -6, -8. All right. And so this is vector V with value. I'm sorry, with components, we're looking for the value of -6, -8. Let me pause real quick. Resume the recording is what I was going to say. Right? Resuming the recording. So what I'm looking for is the length of this vector. All right. A couple of ways to do it. One would be to drop an altitude. I use the term drop loosely because it didn't look like I dropped anything. It looked like I drew upwards rather than downwards. It really doesn't matter what direction you draw the line segment in, as long as it creates a right triangle. All right. Ideally, to be consistent with what we've been doing with unit circle trig, you'd go to the x-axis. Right. And down the line, when we get to polar coordinates, you're going to see why. All right. So that would be a 90-degree angle. I know that this side has a length of -6, and this one has a length of -8. The negative has meaning now where previously it didn't. Right. So the question was about the word of the day. I have not done the word of the day yet. Right. So negatives now have meaning because they're telling us direction. Right. So what this really is, and I'll show you because I think it's important to talk about. I mean, I know it's important to talk about. In this very moment, I think it's important. Right. So if I have a vector going to the left, and that vector has a length of -6, maybe I'll call it vector u, and then another vector that's going in the downward direction, and that has -8, but I'll just call that v for simplicity's sake. Then the resultant, using the tail to tip method, oops, need more than that. Oh, I need less than that. Now let me do this real quick. Not perfect yet using the app, but it's getting there. All right, so using my tail to tip, I would create from the origin a new vector. That would be vector u plus v. All right. So if I tell you that vector u has coordinates, well, coordinates of the endpoint at -6, 0, and v has coordinates at its endpoint of 0, -8, then by the numbers, u plus v would have to be -6, -8, because you add the corresponding parts. All right, so you'd have a -6 plus the 0, giving you a -6, and then the 0 plus the -8, giving you a -8. All right, so that gives us the location, and that's actually what this diagram here is showing us. Now what I want is the magnitude of that. And so I'll put that off on the side here. The magnitude is the length of that line segment. I was able to come up with the location, but I want the length. All right, I have the length of the two parts that make it up, but that -6, that negative sign, that's what I was talking about. has meaning now because it's indicating the direction of the line segment. All that being said, if you follow this relationship here, or you recognize that it's a right triangle, either way, you see that the Pythagorean theorem is in play. So I would say -6 squared plus -8 squared is equal to that magnitude of v squared. All right, because whatever this line segment is in terms of length, it can still be represented by the magnitude of v. All right, let me just fix this a little bit. It looked pretty sloppy. All right, so magnitude of v squared. All right, so we get 36 plus 64, because if you square a negative, it goes to positive. Then if I want to get the magnitude of v by itself, I take the square root of both sides. 36 plus 64 is 100, the square root of which is 10. All right. And this actually helps to justify why in the unit circle, the hypotenuse was always positive. It didn't matter what direction you were going in, whether it was left, right, up, down. The hypotenuse of whatever reference triangle you came up with was always positive. And that's because it really was a magnitude, right? It is the absolute distance that a point is away from the origin, right? And so it forces it to be a positive measure. And besides, you start looking at it as like, okay, well, how would I define positive? If you have something going left, right, up, and down, you could define positive and negative because it's a binary situation, up versus down, left versus right. But if you go off in a diagonal direction, the only way you could identify its opposite would be to go in the other direction. But who's to say that this is what the positive direction would be in a diagonal sense? Maybe it's like this. Or like you could even call this the positive direction. Because there's infinitely many directions you can go in, it makes things, well, infinitely more complicated. Now, if we're going to use the rule, we look at vector V is A followed by B. So you just take the two components, put them under a radical and square each one of them. So in this case, it's radical -6 squared plus -8 squared. And that would give you a 10. You just got to remember that, well, one of two things, either put the parentheses in or just understand that when you square a negative, it goes to positive. All right. So now in part B, it's kind of an extension on our answer to part A. 5 times the magnitude of V, right? The magnitude symbol, magnitude is a scalar quantity, right? You can look at it as a distance, but you could also look at it as a proportional value, all right? Depending on what V is defined as. Bottom line is, in this case, I can just say 5 times 10 because I know the magnitude of V is equal to 10, and so that gives me 50. All right. So it begs the question of like, okay, well, that's cool. Why'd you do that? It's really because of C, where it says find the magnitude of 5V. All right. And so what that would mean, before I said I would never ask you to draw like 45V, like if V is -6, -8, and it has a certain length, you would have to make a new length that's 5 times that. Right? It's not very practical. 45 times was absurd, but even 5 isn't really that practical on using pencil paper. Right? So what we would be doing here is finding, this is the same as saying find 5V, which would be -30, -40, because I'm just taking whatever I have in V and multiplying it by 5, and then applying this same technique. All right. So this is now my new A value, and this is my new B value. So the magnitude of that 5V would be equal to that negative 30 squared plus negative 40 squared under a radical. Now you can do the computation. You get 900 plus 1600. You know, it's not too bad. You know, when you get decimals involved, then it gets a little crazy. But in this case, it's really not terrible, right? 900 plus 1600 is 2500. Square root of 2500 is 50. All right, so that gives us a new rule that it really is. It's kind of a loose application of the distributive property, but it's really just a constant multiple, right? What we're looking at is the relationship that if I have some value A multiplied by the magnitude of some vector V, that's going to be equal to the magnitude of A multiplied by that vector V. All right. And what this ends up being is kind of a time saver, because one technique was a little easier than the other. All right. So if I know V is equal to -6, -8, and I can figure out just by finding the sum of the squares under a radical, that gives me a 10. Then if they say find 5 times the magnitude of V, then I know to take my magnitude of V and just multiply it by 5. Or if they say find the magnitude of, let's say, 10V, right? So like example C, but with a 10 instead of a 5, I could just take this magnitude and multiply it by whatever this number is, and that'll get me what I need, right? So it's kind of nice. All right, so kind of hop ahead here. The rules or properties of vector addition and scalar multiplication, you know, some of them are, I'd say, common sense, but others are, you know, a little out there. I mean, they're all related to stuff that you've seen before, but you know, maybe you wouldn't think that it necessarily works in the context of vectors. All right. So U plus V equals V plus U. That's the commutative property. So commutative property holds when dealing with vector addition. Associative property, same deal. Number 3, that's one of the weird ones, because yeah, U plus 0 is definitely equal to 0 plus U, which is equal to U itself. But contextually, in the sense that we're dealing with vectors, let's say we're in, well, I got to explain this to you in a minute, but a two-dimensional vector, let's say we have U is equal to 5, 4. All right, so that's vector U. And then 0, that's the 0 vector. All right, so when I say 0 is the 0 vector in whatever dimension you're working with, right? Because I have 2 components to this vector, this is what we call an R2. That means 2-dimensional. All right, the R stands for real space, right? Normally, I mean, when you think of all real numbers, it's that funky double R. That's actually what this is supposed to be, but Microsoft Word doesn't really do that nicely. The best it does is some like wiggly, like kind of like that. All right, but this R is set of real numbers. All right, that N is the dimension, number of dimensions. All right. So if I have R2, I'm saying it's in 2 dimensions. Okay, which means that there's an R3 and R4. I mean, you could have an R1, a vector with only one component, but that would be a vector on really just a number line. All right. So if I have, I'll just show you real quick. If I have a vector in R1, real space 1, all right, what that would be is, let's say the example is it's vector V is equal to 2. All that is the number line. You have 0 in the middle, 1, 2. Your vector would just be this. Pinned at 0, going off to the right 2 units to the right because it's positive, right? In 2 dimensions, that's an XY coordinate. We've been working with that pretty much. Now, there needs to be a statement whenever you're adding vectors as to what dimensions you're working with, right? Because you can't add, or at least not easily. There's some ways around it, but it involves stuff that we don't get into in this course. But generally, you're not going to be able to add vectors of different dimensions. All right. So what I'm going to do here is I'm going to say the 0 vector in R2 is 0, 0. So when I find U plus 0, I'm really doing 5, 4 plus 0, 0, which gives a result of 5, 4, and that is what U is equal to. Oh, sorry, U, not 0. All right. So that's the not really justification. It's an example of vector addition involving the 0 vector. All right. Now you can have, let's say, a 2-dimensional vector, and this is what I was talking about before. It does get pretty mind-bendy when you get into higher dimensions, but the instance in which you could add something like the 0, like the vector that I have here 2, with some value vector in 2 dimensions, is by taking this and putting it out to 2 dimensions. All right. So if I give a vertical component and let that vertical component be equal to 0, then what I've done is I've just created a y-axis, but I'm still where I was before. All right. So this would be V in R1. It would still be the same location in R2. V in R2 would be 2, 0. All right. So I'm just basically taking my 2 dimensions, or my 1-dimensional figure, and just looking at it as if it were in 2 dimensions. All right. But looking at something that's 3-dimensional from a 2-dimensional perspective, going down a level, or looking at something that's 2-dimensional in a 1-dimensional perspective, that's a little trickier. I mean, it's a lot trickier. It involves, well, I was going to say technology, but some people can really visualize this pretty easily. Not everybody, though. So there are some apps that'll help you do that, but it can get a little kooky. All right, more on that later. So an example I have here involving the properties: let U and V be 2 non-zero vectors that are non-equivalent, so they're different. Consider the vectors A equals, and I'll write it, 4U plus 5V, and B is equal to U plus 2V. All right. Now, you'll notice that I haven't been doing the little arrowhead things, because when it's defined as a vector, they're saying vector A and implied vector B. We know that whenever I write A now, it's related to a vector. Now, if I need some other variable that I want to call a, because remember on the previous page, we let the components of one of the vectors be a and b, then I would need the markings to distinguish one from the other. I'd have to put the little arrowheads on, all right? But if there's no conflict, if there's no reason to think that a is anything other than a vector, then you would just work with it as is. All right. So find the scalar, they call it lambda, such that the vectors a plus lambda b and u minus v are equivalent. All right. So that's a little out there in terms of what we've been doing. It's like, what is this lambda coming from? But it's really just algebra. All right. So I'm going to set this up because they're saying a plus lambda b and u minus v should be the same thing. All right. So I think I said minus. I meant a plus lambda b. It's kind of like a half x, or an upside down y if you want. A plus lambda b. Well, I know a is 4u plus 5v, and b is u plus 2v. So 4u plus 5v plus lambda multiplied by u plus 2v, that should all be equal to u minus v. All right. So they say it's equal to u minus v. So that's what we're going to say. We're going to agree with that. All right. Now, a couple ways to handle it. One way, I mean, obviously we're going to use the properties, but one thing that we want to be able to do is combine terms if possible. All right. So we can apply the algebra in a way that we can solve for the value of lambda and then use that to figure out how this would all work. All right. The other way would be to kind of work off of these expressions by saying that there's some coefficient that's going to make this into a u, and this, let me just move this over a little bit. This part here into a negative v. Right? So you could do it this way, but it can end up being a little messy. Right? You could already see, I mean, there's like 4 different variables or 3 different variables. Right? But if I know that 4, so I'm just going to draw a line here. If I know that 4u plus something u has got to be equal to just a 1u. And just going back to like the very first time you learned anything in algebra, they use the open boxes to avoid using a variable. I'm basically saying, if I'm going to combine 4 and some number and get a 1, what is it going to be? That number would have to be a -3. All right. And then I would just verify that that would hold for the second computation. All right. So the second computation has 5v plus something 2v. So that something is multiplied is equal to -v. All right. And that's all because all of b is being multiplied by lambda. That something would also have to be a -3. So that means lambda has to be -3. I'm going to show you another way in a sec, because with this topic, whatever method I go with first is usually the method that people are like, all right, I don't like that one, so let me do something different. So it is what it is. And so what I'll do is, let's see. Just trying to think how I want to do it. Yeah, I'll use the equation that I set up here. All right. So this is one way to do it. The other way, I'm going to steal some room at the bottom here, but let me reduce sizing a little bit.
Professor?
Yeah.
I'm sorry, I got a little dazed on this one. Do you mind talking through the word problem itself? Like how you,
Yes.
know, I-
One sec. Just moving some stuff around real quick. Okay, so the example says we have u and v are non-zero vectors. So when he says vectors are non-zero, that means their components are not all zero, right? A zero vector would have every component equal to zero. So instead of being like 2, 4, and 3, 5, it would be just 0, 0. All right. So that's the first thing that we have to account for. The other is that they're not equivalent. All right. So u and v are two different vectors. Right. So one could be 1, 2, and the other could be like 4, 3. Right. They're saying that we have these vectors a equals 4u plus 5v. Right. So that's what I started with over here. All right, just get the highlighting out of the way. I'll just kind of take it from scratch. So these are our two vectors. Now the vectors are also made up of other vectors, right? So there was some base vector u and another vector v that was combined using those diagram methods that we did before to make a brand new vector that we're calling a and another brand new vector that we're calling b, all right? So what they're saying here is that there is some scalar multiple of b that allows the sum of these two vectors to be equal to u minus v. All right. So what I'm saying is, again, two different methods. One method that I showed already. The other is to set up an equation where I'm setting this, the a plus lambda b, I'm setting that equal to u minus v. All right. So that's my equality. What I'm going to do there is make a substitution replacing a with what they tell me a is equal to. They tell me a is equal to 4u plus 5v. So that's where this is coming from.
okay, see.
Right? And u plus 2v, that's b, that's my substitution. All right. So what I can do, this is a more intuitive approach, but what I can do is actually distribute the lambda to each term in the second set of parentheses. All right. So we're going to we'll still have the 4u plus 5v plus lambda u plus 2 lambda v. Multiplication's commutative, so you could write those in any order. But since I want to combine like terms, I want to keep the u's at the end. All right, and that's all going to be equal to u minus v. So I'm going to rewrite. We'll regroup. If you remember factoring by grouping from algebra, this is that without having to do really the factoring part of it. Okay. Well, maybe just a little bit of factoring. So I'm going to take these two terms and group them together. So it becomes 4u plus lambda u. Then I'm going to get a fresh new color here. I'm going to take the 5 plus 5v plus 2 lambda v. I'm going to group those together. So I have a common u. So you just kind of look at this as a little bit of a partition. All right. I'm going to factor out the u here, and I'll get 4 plus lambda. Just make your lambdas look lambda-like, or make them look unlike anything else that you're writing, because otherwise, I'm sure you noticed already, my lambdas start looking like 2s after a while. So you got to sort of be careful about that. And for this one, I can factor out a v from each term. So plus v times 5 plus 2 lambda. That's not a 5, sorry. Little brain cramp there. All right, and all of that is going to be equal to u minus v. All right, so in order for this part to become a 1v, I'm sorry, a 1u, you know, there's that assumed coefficient of 1 here. All right, in order for that part to become a 1u, the 4 plus lambda has to equal a 1. All right, that's the only way it's going to work out, because we structured the equation so that all the u's are together and all the v's are together. And when I solve for lambda, this is going back to early algebra, I get a result of -3. And so that's my answer, that's my lambda. But just to be safe, I would want to check it and make sure it works for the other part of the equation. All right, so I would do the same thing again. Remember, there's that understood 1 in front of the v, so that makes a -v, -1v, I should say. And that has to be equivalent, I'll highlight the whole thing. The 5 plus 2 lambda has to end up being a -1, right? Because we have the v. The only thing that varies from one side to the other is one of them's got a -1 and the other's got all this. All right. So we want to equate that out by setting the 5 plus 2 lambda equal to a -1. So I'd subtract the 5, I get 2 lambda equals -6, and lambda is equal to -3. All right, so in 3 different ways, we verified that lambda is going to be equal to -3. Once you figure it out the one time, you're done. I mean, it's not anything that you need to show 3 different ways for. It's just, it's nice to be able to verify your work. All right. So now we have this magic word coming back into play. All right. Magic. Magic is the first word of the day. As in, some of the stuff that we're learning about tonight seems like it's black magic. Magic is the first word of the day. All right, so we are going to incorporate trigonometry into this, and you'll see the marriage of the 2 ideas and the beautiful math that emerges from it. But in order to do that, we need to talk about unit circle trig again, because we started the last unit with that. We went on to trig graphs, then identities, then came back and grabbed it a little bit to solve equations. Then it's been gone for a little while we did law of sines, cosines, and vectors. All right, so a little refreshers in order. Now, I'm not going to draw the entire unit circle, but I'll just do the first quadrant. So if we assume that this horizontal line, the horizontal line of the triangle goes through the horizontal axis, and the vertical axis goes through the end, that same endpoint, you know, the lower left-hand vertex, call this y and this x. We have, at least if I draw it correctly, part of a circle. Yeah, almost. I'll live with it. I'm just going to move it up a little bit. And I never put my labels in the right place. All right, we have part of a circle with the center at the origin and a radius equal to 1. All right, so this hypotenuse serves as the radius of that circle. Now, if I produce a vector going to the circumference of that circle, that vector is going to have a magnitude equal to the radius of the circle. All right. So this vector magnitude is equal to the radius of the circle. Now, because that magnitude is equal to 1, that makes this the unit circle. All right. The unit circle starts off at 0 degrees or 0 radians. It gets up to 90 degrees or pi over 2 radians, and then it works its way around. But we're only focusing on the first quadrant for now. All right. I'm gonna get rid of this little circle here. All right. So we also learned that any point on the circumference of the circle, well, any point in space is xy, but in the unit circle, that translates to cosine of whatever the angle is theta, comma the sine of the angle theta. All right. So that means that the horizontal axis has to have a value going from, let me do a different color here, going from here to here. The magnitude has to be equal to cosine of whatever the angle theta is. Right. And then going from here to here, the magnitude of this line segment, and we're actually treating them all like vectors now. That is sine of theta. All right. So these are the components of a vector in the rectangular coordinate system. So the ordinary coordinate system that we've been working with. So if I call this vector, I'll call it vector V, then this 1 represents its magnitude. Right? And these two are components of that vector. So vector V would be equal to cosine of theta, comma the sine of theta. And what that tells me is if I know the angle that I want to travel outwards from in terms of either degrees or radians, then I can figure out the corresponding vector. Right. And you see the examples below kind of touch on that. Right. Now, what if the radius is not equal to 1? Right. So in this case, what we're looking at is a scalar multiple. Right. So if I'm in, this diagram got messy over here pretty quickly. So I'm just going to do a quick and short version of it over here. Very, very small. I really got to change that setting. I'm going to live with it for now. So if I have an angle theta in here, this is my vector with a magnitude of 1, and this is cosine theta, and this is sine theta. Then if the 1 is going to become a V, then the way it must have happened, because they're scalars, is the 1 must have been multiplied by V. All right. So 1 times the magnitude of V is equal to the magnitude of V. All right. That's the one of the identity rules. All right. So to get from this length to this length, I had to multiply by the magnitude of V. So it stands to reason that to obtain this length, I'd have to multiply this one also by the magnitude of V. And then this one, in order to become this length here, would have to also be scaled up by the magnitude of V. All right. So in the case of the unit circle, those vectors are always going to have components of cosine theta, comma sine theta. All right. But for any other vector, right, any other vector V, will be equal to the magnitude of V times the cosine of theta, comma, the magnitude of V times the sine of theta. All right. Any other vector V, that's going to be the relationship. And I know the diagram got a little kooky there, but that's the idea, is that we always start off with the unit circle and then scale up from there. All right. So if I know, instead of the radius being 1, like I have over here, if I say the radius is 20, instead of having cosine theta, sine theta be my vector components, it would be 20 cosine theta, comma, 20 sine theta. All right. That's what I was talking about before. The lead into this was that example where we found the magnitude and then we multiplied it by 5. All right. That was to show that whether I extended the length of the vector by a factor of 5, or if I just multiplied its magnitude by 5, ultimately it ended up giving the same thing. Now, for many of us, it's like, okay, new rule. Okay, that might be all you need. All right. Because when you look at the examples that follow, it's really not anything too crazy. Calculator becomes pretty helpful. If you know that this rule applies, when you're looking for the component form of any vector, even a vector with magnitude of 1, right? Just like in that first diagram, it's still going to work. We have a rule that says any vector V is equal to the magnitude of V times the cosine of theta, comma, the magnitude of V times the sine of theta. All right. So if I tell you that the magnitude, they say there's a vector of magnitude 4. So let the magnitude of V equal 4, and it forms an angle of negative 45 degrees with the axis. And I'm going to say theta is negative 45 degrees. Or if I want to stay positive, I could say 315 degrees. All right, you can go either way with that. Since we're going to do it in a calculator, it doesn't really make a difference. So I leave that part up to you. But in determining the actual component form of vector V, I'd have to substitute these values in. 4 cosine, I'll go with negative 45 degrees. And then 4 times the sine of negative 45 degrees. All right. Then we just crunch these numbers and we have our vector V. All right. And so at this hour and 20-minute mark in the class is the first time I'm going to touch the calculator. It's kind of atypical. And it doesn't always happen like that, but you know, it's kind of nice. Kind of nice to get away from the calculator for some problems. You'll notice my calculator is in radian mode. So I got to go home, down to settings, change it to degree mode. All right. Then I could do all my work without fear of any issues emerging. So I'm going to type in 4 cosine negative 45. Good thing about numworks, again, is that it gives you not only the decimal value, but the nice radical value. So 2 radical 2 is my first component. Same deal, 4 sine of negative 45, negative 2 radical 2. Now, the decimal values are also kind of helpful because even though this question is not asking you to draw a graph, this tells me that if I plot, I'm going to the right and I'm going down. So that tells me that I'm looking at some vector pointing off in this direction. And that is consistent with 315 degrees, or if you're looking at it as negative, remember negative is going in the clockwise direction. So it does appear that we've traveled somewhere in the neighborhood of 45 degrees clockwise. So there's no reason to doubt these values are accurate. All right. The next one's really the same concept. So vector V is equal to, again, magnitude of V cosine theta, comma, magnitude of V sine of theta. And we're going to let magnitude of V equal 10, because it says it in the problem. Nobody asked, but I got to imagine it's like, why are you letting the magnitude of V be equal to 10? Because it says find the component form of vector V with magnitude 10. All right. And we know that the theta value, they told us that, is 120 degrees. So vector V is going to be 10 cosine 120 degrees, 10 sine 120 degrees. All right. So then we put these values in and we get our result. And again, calculator is really nice. 10 cosine 120, 10 sine of 120. All right. So -5, comma 5 radical 3 would be my vector in component form. All right. But we do have to talk a little bit more about unit vectors, right? Because well, I've been calling them unit circle vectors, but they're vectors of unit equal to 1, right? A single unit, right? So vectors whose magnitude is equal to 1. Right? There's a shorthand way of writing these, although it's not very shorthand. I just feel like it's more technology friendly. And I'll get to that in a minute. Because when you're typing mathematically, you know, doing these arrow brackets and the double, you know, well, the double verticals aren't a problem, but, you know, like all the notation that we develop here, thetas and all that, it's tougher to do using, like if I were to type something in Microsoft Word, which all this stuff was from, it's not the easiest thing, but representing our vectors in a more algebraic way tends to be pretty useful. So we'll get to that in a little bit. Maybe not tonight, but eventually. So a unit vector, again, is a vector with magnitude of 1. And this little statement here has to be made, even though it's very rarely going to work against you, for any non-zero vector V, right? So a lot of things fall apart if zero's involved. Like, for example, I can divide any number in existence by any number that I want. Oh, wait, if I divide by 0, it's undefined. Well, that doesn't work. So what you do is you make a statement saying, all right, you could divide 2 by x as long as x is not equal to 0. Then you're good. So we want to make the statement for any non-zero vector. Don't let that get in the way. It's just saying you have some vector V that's made up with numbers other than 0. It could have 0 in it, but it can't be entirely 0. All right. We can use scalar multiplication to find a unit vector that has the same direction as V. And basically what we're doing is we're scaling down whatever vector we have so that it only has a magnitude of 1. Sometimes it creates fractions, or most of the time it creates fractions. Sometimes the fractions are hideous. All right. So you just got to kind of bear that in mind. But fortunately, the numworks takes care of a lot of that for us. Now, these two right here, these two vectors are our unit vectors. All right. So it's at the point 0 that we start each of our vectors, as we know, or 0, 0 if it's two dimensions. But then the terminal point gives us the location of the vector and its orientation. All right. So I don't know what happened to my notation here. This got a little out of whack. I don't even know. We're not even in this unit or this course. Well, I clicked the wrong thing. And I got these stray marks here. That's not good looking, but this is 1 unit to the right. Its vector value, or vector in component form, is 1, 0. So what we do is we let I equal the vector 1, 0. All right. This vector here has an endpoint at 0, 1. So we let J be equal to that. All right. Now, if I were to create the resultant of this, remember the tail to tip method? So I'm going to take a duplicate of this vector here, slide it up. And then connect it with the origin. So we get a fresh new point over here, connect it with the origin. We could call this vector, we can call this 1, 1 for a couple of different reasons. One, because when I used my graphical approach, it placed the endpoint at 1, 1, but you could also add the two components. Again, that's 0 plus 1 gives you 1. 1 plus 0 also gives you a 1. All right. Now, with that being said, in order to get my resultant vector, one technique was to add the two component vectors. All right. So I had this vector here added to that vector there. Well, and so I'll just write it up here. I did 0 plus 1 plus 1, 0, or vice versa. It doesn't matter. Actually, I'll do it the other way around. 1, 0 plus 0, 1, and that gave us a result of 1, 1. But over here, I'm saying that I is equal to 1, 0, and J is equal to 0, 1. So I can actually call this, instead of saying 1, 1, I can call it I plus J. All right. Now this unit vector, that is the sum of, well, actually, I'm sorry, this vector, which is the sum of unit vectors, can be scaled. It could be scaled upwards, it could be scaled downwards. But it allows us to create multiples, and that's how our coordinate system works. If I say that I want to plot a point, so plot just the ordinary coordinate 2, 3, what I'm doing is following the recipe where it says take 2 1-unit movements to the right because it's positive, and 3 1-unit movements up, again because it's positive. All right. It looks like I'm saying 2 minus, so let me fix that. Just do it this way. 2 So 1-unit movements to the right and 3 1-unit movements up. All right. So if I wanted to plot a vector, it would boil down the same way. But what this is getting at is the idea that we can create a vector whose magnitude is equal to 1 and use that to get us to any point in the coordinate system just by finding scalar multiples of that unit vector. All right. So I'll give you a quick example. Let's say I'll use vector 2, 3. And I'm going to use this formula, U equals 1 over the magnitude of V times V. All right, you could also call it V over the magnitude of V. Doesn't matter. Same thing. I'm going to call this 2, 3. I'm going to call that vector V. So the magnitude of vector V, we talked about this before, is what you would get if you squared each part, added them together, and then took the square root. All right. Simple computation. Sometimes it gives you a disgusting radical. So we get the square root of 13 as the magnitude of vector v. Now u, unit vector u, u is equal to 1 over magnitude of v times v itself. All right, magnitude of v, clean this up. Magnitude of v is radical 13, so 1 over radical 13 multiplied by 2, 3. And I can distribute if I want, really doesn't matter at this point, but I will, just to give you both versions of it. You would get 2 over radical 13, comma 3 over radical 13. Now, I don't see a single 1 in here, so I might be thinking to myself, all right, well, that ain't right. But what we're saying here is that the magnitude of this vector is equal to 1. All right, so if I applied my magnitude process to these numbers, I'll just do it in the calculator, I should get a 1 as a result. All right, so what was the process? I square each one of them and I slap a radical over it. So I'll do the radical first, square each one. So 2 over radical 13 squared plus 3 over radical 13 also squared. Oops, well, I'll put the 2. So this should give me a 1 when I find its magnitude. And so I hit OK, gives me a 1. So I now know that I have a vector that points in the same direction as vector v, but only has a magnitude of 1. Right? And this is really like the beginnings of linear algebra. And we do a lot of this in Calc 3. So it's like, why are we learning it now? Well, I might have mentioned this before. We do all the pre-calculus stuff to get you ready to handle calculus. The problem is some of the stuff you don't see for a couple of semesters, right? But the idea is that it should be a little easier the second time around. That being said, you might forget all this stuff. That would stink. But at least if you have some kind of working memory of it, it'll be okay. And then the other aspect is, if you're not taking any of those classes, then you're learning for fun. And that, depends on how you define fun. That could be a good or bad thing. Who knows? All right. But let me just do a quick diagram, because that seems to be the theme of this part of the unit. All right. So quick diagram over here. Here's 2, 3. That was the magnitude, I'm sorry, that was the vector v, which has a magnitude that we didn't figure out. Oh, we did. I'm sorry, it's right there. It's radical 13. All right, so this has a magnitude of about 3.6. Right, and so when you look at the distance going from here to here, I suppose that could be about 3.6. Now, what we just figured out was a corresponding vector that had a magnitude of only 1. All right, so in decimal form, 2 over radical 13 and 3 over radical 13, they're not pretty. We got about 0.6 and 0.8. So this is about 0.6 comma 0.8. If I plot those, and this is my u, the unit vector that we're calling u, all of this stuff is the extension of that. 0.6 would be about right here, 0.8 about right there, going up to the line, connect. we just figured out this little tiny vector. All right, so I can scale this vector any way I want. I can multiply it by 10. I can multiply it by radical 13 if I want. And it'll always put me on the vector going in this direction, unless I multiply it by a negative, in which case it flips the direction, right? But what this ends up giving us is what's known as the basis of this vector system, right? And I don't want to go too far into linear algebra, but if we define 1 as being this length, then we can count in terms of this length. So if I say, give me 15 in the universe where 1 unit is what we just drew, then you have a basis for plotting out 15 units in that direction, right? So what we're really doing is redefining what the number 1 means in a geometric sense. All right. 1 is not always equal to 1. 1 is whatever you call it, because as you know, when you scale a graph, like I did here, I called this distance 1. Right. So everything else was predetermined based on that choice. Right. This distance here ended up being radical 13, but it would have been radical 13 if I put my 1, instead of putting it here, let's say I put it over here. Let's say I call this 1. Then I'm counting 1 unit, 2 units. I get a much larger graph, but the magnitude of the vector is still going to be radical 13. All right. So it's a lot to kind of wrap your mind around, but the idea that we could redefine number systems according to whatever our need is, that's pretty important. Because I mean, you just think about it this way. You take a pill, it has a certain dosage. You may not know what the dosage is. But if you take 2 pills, you know you're getting twice that dosage. So what do? We define 1 pill. 1 is equal to the number of pills. But that 1 might be 3 milligrams. Right. So what is it equivalent to in another number system? Because I have the units of pills, 1 pill, 2 pills, 5 pills. 5 pills is 5 times the number of pills if I'm only starting with 1. If I have 30 pills, that's 6 times the number of pills I have if I only have 5. But if I then know that 1 pill is equivalent to 5 milligrams, I can now, instead of thinking in terms of milligrams, I can think in terms of pills and still know how many milligrams I have. All right. That's a very basic example, but involving graphics, any kind of scaling of anything really, it really has a lot of applications. I mean, you're not going to sit down and run these numbers every time, but you have to have a sense of it in order to be able to do that kind of stuff. All right. So, and you know, like even something as simple as when I was driving in the car today, I had my radio on and I had it on 2. Like, what's 2? Well, whatever Honda defined 1 unit to be, in turn, you know, those little bars as you hit the up arrow, little bars come up, and 30 is the maximum, and 0 is the minimum. Obviously, you might have no volume, but 1 is what they predetermined to be their volume space. So when I have it at 5, it's 5 times whatever they determined to be 1. But I don't look at it that way. I look at it like I'm going to increase the volume to whatever I want my volume to be, or whatever doesn't hurt my ears and still allows me to hear it. So not too low, not too high. So maybe on their scale, my 0 is 10. And maybe I look at every 2 steps on their scale as being, okay, well, increasing the volume by 1 step doesn't really mean much to me. It really starts meaning something if I increase it by 3. So now 3 on their scale is on my scale. All right. So it can be a little mind bendy, but it is a matter of perspective. Like any sort of application you can think of where you redefine the baseline based off of your own perception as opposed to the author or the designer of the technology, whatever. It really could apply to anything, this concept, right? So that's actually enough to I didn't give a second word of the day. I'll do a triple one next class, so just be on the listen for that. But I think that's enough for today because I don't want to overdo it. I know I'm on the borderline of having overdone it for tonight, but I want you to be able to digest this stuff before we continue on with it, because we're going to get into the applications of this, which ties it together with what we were doing with the law of sines and cosines. So that's where we're going to leave it for tonight. If you have any questions, stick around. Otherwise, enjoy the remainder of the evening, and I will see you on Monday. And if you came in late, check with me before you go, please.